Welcome back. So in the previous video we went through an introductory video about file systems, and we just discussed about different components and like what problem it's trying to solve and like what's the point of it anyways. And so before moving on to actually learning about how we store or read files in the file system, I think it's more important to actually understand the data structures used in the file system to organize itself. Okay, so let's first of all see what was the overall organization and the layout of the file system, right? And how it logically basically splits, first of all, the disk into blocks, into fixed size blocks, usually 4 kilobytes. It's very common to use that number. And also the different regions within this organization, right? We can say that there are 5 main regions: the superblock, then there are 2 bitmap regions, one for inodes and one for data. We'll come to them later. And we also have the inode table region, and finally the data region, where it consists of all the data blocks. So let's make this more concrete and go through this example. Let's assume we have a 64 block disk, right, which looks like this in the diagram. The first block is obviously the superblock, which is very important, and then we have one basically block for the inode bitmap and one block for the data block bitmap. Then we give and allocate 5 blocks for inodes, right? And the rest is actually used for the data, right? So all of these are data blocks which will store our files data, for example images, text files, and so on. So now we have the first important data structure, the superblock. As we discussed, it basically has the global metadata of the file system, right? The metadata of the file system itself, in other words, such as the number of blocks, the number of inodes, the starting location of different regions like the bitmaps, and so on. That's why it's the first thing actually that the file system reads when we mount our file system onto a folder or whatever. It's very important because it's like the starting point, and the file system will know how things look like, let's say in the different parts of the disk, and it can like calculate different things. And so that's about the superblock. But before we move on, actually let me show you something. So this is actually the wiki page in OS Dev. Feel free to check it out. This is the wiki page of ext2, or the second extended file system, which is like an older file system used in Unix and so on. It's a very simple file system. It doesn't have a lot of the journaling or the more advanced features that, let's say, ext4 or ZFS has. But anyways, we want to actually just see what are the superblock fields to just get some idea about it. So you can see that we have like the total number of inodes, the total number of blocks, total number of unallocated blocks. It's a very long list of different fields, right? So feel free to check it out for other stuff. I think we'll come back to this for inodes as well, but let's move on. Okay, so now we come to the bitmaps. Again, a very simple data structure, nothing like impressive. Basically, each of the bitmaps for inode and data respectively will, like, we have a bit vector where each bit represents, let's say, a data block or an inode block. So let's say if we have data block 50, right, and it is allocated, so it's used by some file, then in the bit vector we have the 50th index set to 1, right? Otherwise, if it's set to 0, that means that that specific data block is free and can be allocated for a new file. The same thing happens with inodes. We can know which inode is used or not. And since we have only one block allocated for, let's say, data blocks, you might be wondering, is it enough or not? So one block is 4 kilobytes, right, in our assumption. And if we just multiply it by 2 to the power 10, right, 4 times 1024 times 8 like bits, right, we have around 32,768 bits, right, which we can allocate in one block, meaning we can handle around 33,000 blocks or 33,000, inodes, which is more than enough, at least in our case, an example. Okay, so now let's talk about inodes. Last time we went through them, but it was very high level and abstracted. We're going to get more in depth now and do some calculations as well for reading a specific inode block. Anyways, as we discussed, inode is essentially a low-level representation of a file. So a file name, let's say, I don't know, main.py, is mapped to some low-level number, or in other words, an inode number or inumber, which that inumber or inode with that specific number contains all the required data of the file, such as the size, the permissions, the number of blocks used, and most important of all, pointers to data blocks, so we can know where the data is actually stored. So, as we said, we have to kind of organize inodes somewhere. We have a specific region of inodes, which is the inode table. And again, you might be wondering that if only 5 blocks of inodes is sufficient to handle, let's say, again in our example, 56 data blocks. And the thing is that we have 4 kilobyte blocks. However, inodes are usually around 128 or 256 bytes. So assuming we have 256 byte inodes, we can have 16 inodes per block, right? If we just divide 4 kilobytes by 256, we have 16 inodes that can fit into one block. Meaning, with 5 blocks in the inode table, we can have a total number of 80 inodes, which is more than enough because we only had 56 data blocks. So in the worst case, if we had one inode for each data block, we still have more inodes left. Okay, so now let's go through an example to make it more concrete in our minds of how things work. So assume we have this basically structure, right? So you can see that this inode block or I block 0 is basically contained with or consists of 16 inodes, the 0th inode until 15, and so on. Now we want to read, actually, let's say the file system wants to read the data within inode 32. To do that, right, the superblock, to do that we have to actually compute an offset from, let's say, the first inode, right? So to do that, it's very easy. We just multiply 32 by the size of our inodes, which is around 8 kilobytes. So that means that if we add 8 kilobytes to 12, right, we have 20. So this is where 32 is, right? And the superblock already tells us where the inode region or the inode table starts. So we already know 12 kilobytes is the initial offset to the inode table, and the extra 8 kilobytes is the offset to that specific inode we want. Okay, so we already talked about that inodes have pointers to the data blocks, such that so that we can actually find out where the file data is actually stored, let's say an image. And the thing is though, we can have direct pointers, which is very easy and convenient. However, we will see in a bit that only direct pointers will not be sufficient because they can only handle a limited number of file size. We can't have, let's say, a file size of multiple megabytes even with only direct pointers. And we can't have a lot of direct pointers because then it will be inefficient. So to kind of solve this issue, we add layers of indirection. So as you can see in this example, if we only had direct pointers, usually the number of direct pointers is 12. So here we are assuming 12, and we'll see actually again in the ext2 wiki that it's even 12 there. So with only 12 direct pointers, we can have a file size of maximum 48 kilobytes, which is not so much. That's why we need to add extra layers of indirection, like the single indirect pointers. And to do that, let's first calculate how many pointers can one block contain, right? And assuming a pointer size is 4 bytes and the block size is 4 kilobytes, then if we just do a simple division, we can know that we have around 1024 pointers per block. So let's do some extra calculations. Let's say we have the 12 direct pointers, right, and then we have a single indirect pointer that points to a block containing 1024 or 2 to the power 10 pointers. This means that if we multiply these by 4 kilobytes, we can have a file size of maximum 4 megabytes. It's around 4 megabytes. And for a double indirect pointers, we'll have 12 plus 1024 because of this single indirect pointers, and we will have 1024 to the power 2 times 4 kilobytes, which will give us around 4 gigabytes of files. Like, we can have a file with maximum size of 4 gigabytes. And then finally we have the triple indirect pointers, which basically we have, again, you can see the pattern here, 12 plus 1024 until we have for the triple indirect pointers 1024 to the power 3, right? And then when we multiply this by 4 kilobytes for each block, we have roughly around 4 terabytes. This is, I think, approximated. It's not really accurate, but still, just keep that in mind. I think it's more than enough to have 4 terabytes. Yeah, so let's go back to this wiki just to see, how inode looks like. You could see that in ext2 even we have, again, the metadata part, for example. We have type, permissions, user ID, creation time, last access time. And here you could see we have the 12 direct pointers, right? And then we have the singly indirect pointer, doubly indirect pointer, and triply indirect pointer. And I think, yeah, that's basically the maximum. We have some extra metadata which is like specific to the file system itself, but that's like not so relevant. But yeah, before we move on, let me also show you this. So you could see that inode types are kind of specified in its own field here, right? Type and permissions. And you could see, for example, we can specify whether this inode represents a directory or like a regular file or even a symbolic link. We talked about this very quickly in the last video, and we're just gonna go through it again because we're gonna now talk about directories. So directories, as we just said, they are inodes that have a specific type, the directory type, right? And the idea behind a directory is that a directory kind of points to data blocks, and within those data blocks we have directory entries, which basically the point of the entry is to keep an entry name, which is the file name, let's say, or a subdirectory name, and their own respective inode number, so that we can trace that inode number and see, for example, what that file contains or what that subdirectory also is pointing to. But also we have some additional metadata like record length. Let's see. You could see this diagram again, and here we could see that we keep some metadata obviously, but then let's say the direct pointers points to data block 0. Here we have two special, all directories, as you might have noticed in like a Linux or a Unix environment, we have two special directory names, dot and double dot, which points to the directory itself we're currently in, or its parent directory, right, in the hierarchy, if you imagine it. And then we have, for example, let's assume this directory has some file foo, right? You can see the inode numbers. So this is pointing to inode number 5, which is itself. This is pointing to inode number 2, which is the parent directory, some other inode, right? And this is pointing to inode number 12, which this inode would be a file inode, not a directory inode. And let's assume this is the maximum size, and then like it stores its like fourth file or second file, sorry, and its fourth entry, into a separate data block, right? So that's basically it. With indirect pointers, it will look something similar to this, but then we will have, again, layers of indirection to handle more and more entries. So this kind of wraps up our discussion about the data structures used. We talked about the logical structure of a disk, the metadata in Superblock, bitmaps, inodes, and the data region. And basically we try to understand what data structure does the file system use to organize data and metadata, and to actually, try to figure out how to work its way around the disk, right? And this pretty much sums up this video. Thanks for watching.